Okay, Sultan, you can start in 3, 2, 1.
Hi everyone, my name is Zoltan. I'm chairing this session here on behalf of the BIPSA Education Committee. And I'm inviting you to our talk today by Dr. Alex González Cáceres, who we'll hear from in a minute. Before we do that, quick reminder, what the Education Committee does is identifying education and training needs for our community and also initiate, develop, and encourage such educational material to be disseminated. And part of that is training sessions such as this one, and also development and sharing of best practices, again, such as this one, when we hear from members of the community. This is the third presentation in this talk, in this series. We have all of the other ones that came before this one and also that will come after this one will be on YouTube. And so you can always watch them when you want. The next two or the final two are in 2 weeks, Dr. Faulkner, and then finally the guest editors of this special issue where these talks are coming from will be on June 26th. And with that, oh yeah, you can sign up for the Best Practices Network and support us for a couple of lattes a year. Very easy. And with that, Alex, can you please share your screen and begin your talk? And as we discussed, you can introduce yourself um, for this. And right now we cannot see you and you are muted, so maybe we can change that too. Alex, you are muted. Oh, there we go. Okay, very good.
Thank you very much for the invitation.
Your talk is not in presentation mode yet.
Okay.
So let's try that again.
Maybe now.
Yeah. Let's try that.
Is it working now?
You're good to go.
Okay. Thank you for the invitation and for organizing this webinar series. It's been very interesting to see the presentations. I will introduce myself. My name is Alex González Cáceres. I work with wind and performance simulations, and now I'm exploring how to uh, bring simulations into digital twin. And the project that I'm going to present today is part of the work that I did while I was in Chalmers University. This project is interdisciplinary research with different experts and different domains. And the paper that I'm talking about and the name of this presentation is Towards Digital Twinning for Multi-Domain Simulation Workflow. And this is a case study in Gothenburg. And the motivation to do this project was to develop a pipeline where we can use different lenses to analyze urban environment and concentrate all the results and work in one workflow. Also, where we were doing the literature review to see previous works, we noticed that it's seldom that you see this type of connection between simulation programs. And that was also part of one of the motivations to do this research. The outline of the presentation, I will first talk about the paper that I'm presenting now, followed by an introduction, where I just simply want to explain a little bit about digital twin and the concepts that we were using during the presentation. I will present the case study methodology, followed by the results. And also want to present my current work now, which is the link between simulations and digital twins. I will just do a very brief explanation of the methodology and the current results that we have, and I will finalize with the conclusions of both works. So As I mentioned before, I just want to explain a little bit why we are using digital twins and how is it connected with simulations. So when we talk about digital twins, we are talking about a real environment, object, or component or system, and we create a replica or a virtual environment. And the main characteristic is that replica is connected and can bring data on real time. And that information it can be used to train algorithms or for machine learning and simulations to have a better understanding how the real world works. And in this case, cities, which are complex organisms. And here I'm using the concept of Alvin where they explain the different complexities of digital twins. So in a first step or the most basic form, it would be the passive digital twin, which is development of the replica, and it can have different degrees or of complexity. We call it level of detail. So we can start with terrain, for example, but then build up to a different complexity of the geometries. If we include architectural feature into the model. But at this level, even if it's a very complex and detailed construction of the replica, it will still be passive because there is no interaction with data. So the next level of complexity in digital twin, they call it predictive digital twin. And that's when the data comes in and it has two stages. We can process that information, run simulations on machine learning to better understand how actually works the city. And a level up, it will be to introduce scenarios and to perform predictions based on calculations. And in this way, there is information that comes from the real world into the replica, but it doesn't go back. So will be the second stage of digital twin. And in other papers, this concept is also called digital shadow. And actually, this is more close to what I'm going to present today. And the third level is when we have a back and forward of the information. So we run the simulations with the virtual environment, and we inform about changes that can be done in the real world. And the most complex stage of the digital twin is when it's programmed to make decisions by itself and control the real aspects of the city. So we can optimize on real time energy production, transport, or other systems that require immediate changes. The case study that I want to that we use in the paper is in Gothenburg, Sweden, and a specific neighborhood is called Givaltavalen. And this area has special attention because the municipality has said that they want to densify this area since there is a lot of parking lots. And here we can see um, one of the sketches of the idea of how that area can be transformed. And what we did to simulate how these buildings can impact on the existing environment, we developed different alternatives of architectural designs that can be placed in this area. We actually develop grasshopper codes that build and construct alternatives under several constraints, so we can have comparable designs. So one of them was the area, all the design alternatives to reach 5,500 cubic meters, and also they can reach up to 7 floor height. So the model or the Grasshopper code, it developed maybe 1,000 combinations, and we picked the ones that were more architecturally sound, and they look more realistic of what the changes were going to be there. There were some challenges while we were developing the workflow. One of them was to gather the geometry of the Gothenburg city to define the alternatives as well. Require some conventions between the different teams. And I think the most challenging part was interoperability of how we exchange the files, because we are working in different environments with different tools. And also each type of simulation require different standards and inputs. Then we run simulations with the different solvers. And also it was a challenge to combine the results and how we can visualize the data, since we are all working with different softwares. More in detail, this is the pipeline. The 3D model was obtained through DTCC Builder. DTCC is a digital twin city center of Chalmers. And they developed the model of Gothenburg using LiDAR data, which is available, I think, by request. And then this is a national level, so the data is for the entire Sweden. And I think what they do is they clean the point clouds, and you can discover the volumes of the buildings. And that, in combination with the building footprints, they generate the 3D model of the entire city. And that file is the one that we share across the different domains. That file was divided in different layers, like ground, city model, each building, and it was analyzed and cleaned through Grasshopper. That requires some manual work because since we were focusing on a neighborhood, and each type of simulation needs a different scale or range of the city. For example, for wind comfort and wind speed, the area of impact is much larger than for acoustics. So to save computational time, we manually clean the 3D model for each domain. The next step is after we exported the file and the same file in different formats, we run the simulations with 3 main solvers for wind comfort, energy, solar radiation, and noise. And finally, we organize a way to compare the different results and score them, so we can define which alternative will have the best performance. And finally, we use a visualizer that was tailored for this project, where we can put together all the data and results, so we can make sense of the result. Also, we can share the data with others. So as I mentioned before, we use 3 solvers. For the wind speed and wind comfort, we use EvoFlow, which is a tool developed in Chalmers, and it's been validated for urban wind simulations. This tool was coupled with Energy Plus to calculate the pressure coefficients, which have an impact on the infiltration losses. For the energy simulation, we use Energy Plus, as I mentioned, and also Honeybee. The inputs that we use were based on standards such as ASHRAE, and also we share the same weather file. And for the noise calculations, we use the northern prediction method, which is a local standard for traffic noise. And these calculations were done through MATLAB and Python. And as I mentioned before, we couple the wind speed with the energy simulations to have a more accurate result of the impact that these different alternatives will have. So what we did is to calculate the pressure coefficients for the base case scenario and also for each alternative. So that gives us a sensitive parameter that impacts when the buildings are high or there are even open areas where the wind tends to be stronger. Now I'm jumping into the results of the energy on simulations. What we see here is the base case scenario where there is no buildings, and we calculated the energy consumption for the surrounding buildings. We initially calculated for a larger area, but we saw that was no impact. So what I'm showing now is the one that actually have changes. And when we compare the alternatives against the base case scenario, we saw that all the alternatives, they have a negative impact on the heating demand of the surrounding and the existing buildings. However, there are alternatives that produce less consumption, and that will be alternative 5. And later we convert this impact into percentages, so the values are normalized and we can compare them through different domains. To have a better understanding why the energy demand was increasing, we run solar radiation simulations because the main factor besides the pressure coefficient and the infiltration was the shadowing produced by the different alternatives. And we noticed that one of the main factors on the shadowing was the height of the volumes and the proximity towards the existing buildings. So what we see here is the base case scenario with the solar radiations. And the other plots, what they are showing is the opposite, is how much solar radiation was taken because of the new buildings that were going to be placed there. So the reddish, the color, it means less solar radiation was in place because of the shadow. And this calculation was done on a yearly level. For the noise simulations, we have the base case scenario, and there is like a straight line, and that's where the traffic goes. Based on the results, the base case shows that the noise propagation is quite high. And when we run the alternatives and the new designs, we notice that all of them, they impact positively in the surrounding environment. There is a reduction of up to 9 decibels in some spots. And this shows us that depending on the configuration of the volumes, the impact can be greater. The best alternative, it was alternative 1 and 5, with they reduced the noise traffic up to 35%. And for the wind comfort, we use Lawson DDC criterion, which refers of how the local conditions and the wind speed impact on pedestrians under certain activities. So in the base case scenario, the results show that the wind comfort was relatively okay, except for some spots where it's more suitable for standing rather than sitting. And yeah, there is also something I forgot. The wind comfort, like the higher the activity, the more energy consuming activity, the higher wind speed you can take and be comfortable. So if you're sitting, you will be more susceptible of high speed. So that's why standing is more energy consuming than being sitting. So according to the results, this was very similar to noise. All the alternatives that we tested, they impact positively in the wind comfort, especially the configurations they provide shells to eastern wind direction. And in this case, the best alternative, or the ones that have a better wind comfort conditions, were alternative 5. When we put together the results from the 3 domains, we noticed that it wasn't an alternative that will perform best in all the domains. But since we normalize them, we were able to compare them and to pick the ones that score the highest. That will be alternative 1 and 2. And one of the things that we also saw from the result is the energy and wind, and all the alternatives, they score positively compared to the base case scenario. However, energy demand, it was negatively in all the cases, except when we take into account all the cooling, where it was one alternative that actually reduced the energy demand. And the results are synthesized in the last image, where we can see that the bars that goes to the right, they improve compared to base scenario, while if they go to the left, that means that they have a negative impact. And as I mentioned before, we developed this visualization tool where we can plot the results and compare the different scenarios. This was useful for us to understand better the data, but also to share the information with others that are not into simulations. So other stakeholders were able to interact with the data and test how different alternatives can impact existing environment. Now I want to show the current state of the project, and this is the area that I'm that we were looking now. Oh, I cannot. Oh, yeah. Okay, sorry. Maybe now it will work. Okay, sorry. Yes, this is the area that we were studying in Gothenburg. This is near Chalmers University, and we can see the area of where the different alternatives were tested. And this tool that we are looking at now is one of the projects that I'm working currently, which is a workflow to develop digital replicas for cities. So we don't only take into account the geometry, but what we are trying to add in the pipeline is how to connect real-time data into the 3D model. What we're seeing now is the results that were already computed from the previous work. As it is now, the tool is designed to import data if it's correctly formatted, that it can be placed, if it's geo-referenced. So now what it's showing is the noise calculations. I will speed this a little bit. We also added into the tool the options to perform simulations. Since the tool originally was designed to evaluate built environments for specific users, which is agent population. And for that, it's important to include thermal comfort and wind speed. The tool, what it does is to compute silently the simulations, especially energy demand. And that's one of the challenges that we have now, because it works on tiles, and depending on the size and the complexity of the buildings, the simulations can take longer than the resolution of the data transfer. So normally the weather data that is captured is every 15 minutes, but we are trying to solve so the simulations are updated every hour. Okay, so, I will just briefly show the wind speed simulations and thermal comfort. It was also important for us since the tool is was think not only for expert, but to show data and turn it into information. So the interface and part of the calculations also modify the model, especially the weather data. So depending on the weather conditions, the 3D environment will change. For example, this is winter. It can the lighting also change during the day for sunset, sunrise, and it has it calculates the shadowing also based on the cloud cover. So we use this tool, as I mentioned originally, is intended to analyze urban environment, but under the lens of senior citizens. And the case was there was use. It was Gulheden. It's also in Gothenburg, and this area has a particularity as it has a higher density of seniors. The average in Gothenburg is around 50%, but while in Gulheden is almost 24. And also it's a challenging area because it's quite hilly, but it's built with a lot of facilities that are important for aging population. And the metrics that we use to incorporate in the tool is accessibility metrics, thermal comfort, lighting and visual environment, safety hazard interaction, mobility supports, and social environmental well-being. For some of them, we don't need simulations. It's calculation based on the data that is captured while we are producing the replica. But for the thermal comfort, we use the indoor environment of each building, the energy demand, to calculate the energy level of the buildings, and thermal comfort, which is calculated on the surroundings of the neighborhood. To build the tool, we use three different sources of data. First, we use satellite imagery to calculate the layout of each building. For the window detection, we use Google Street View and LiDAR scanner. This was ground. LiDAR scanner was an aerial, and we use it more like for verification to check if the calculations that were done with Google Street View were correct. And then we process the layout of the buildings and the first roof that is detected through the satellite imagery. And we use a code pipeline, which try to mimic what the architect was thinking when they designed the roof. So based on mostly architectural logic and the shape of the building, we add some helpers to fix some of the gaps that or issues that the satellite imagery roof had. And for the data enrichment, we use open source databases such as OpenStreetMap. Also in Sweden, there are these public record aggregators which contain information of the population. And there are also some internal calculations. Once the buildings are built, we can enrich the data of each building, for example, the height, if it has a basement or not. That information is added into the internal database. For the urban environment detection, we use Google Street View for identifying the different elements that we don't have in the OpenStreetMaps, such as lighting or stairs, handrails. For the ground detection, we use the satellite image combined with Google Street View. We didn't use the one from OpenStreetMaps because there was a lot of difference between the one that we calculated against the one from OpenStreetMap, and we rely more on the on the one that we calculated, but we have the option also, if we see that it didn't work, we have a rollback and then go into and use the OpenStreetMap mesh for the ground. And also there is another code of in Python where we need to merge the different objects and elements that we found because we are using different sources. And what the codes are trying to do is to select which one is more likely to be the correct one, because not all the different sources agree. And with that information, and we prepare our database, which is a JSON file. For the data enrichment, we also use OpenStreetMaps. We use weather stations for each tile. So we prefer to use the ones that are inside the tile. If there is no one, we use the closest. And also we connect the public transportation through a database from To-Go, the faster traffic, where we have access to the different public transport that are in place, and we can add them into the tool. These are two different results. The one from the left is the 3D model that we get from the photogrammetry, and the one from the right is when it was our old pipeline. We were just trusting in OpenStreetMap data, and we use the helpers that I mentioned before, the architectural code that they try to understand how roof works. But we noticed that there are some difference, not only in the design of the buildings, but also the orientations. So they are not quite the same. And I think the satellite image is more accurate. Another challenge is the computational time. They take us, well, I mentioned it before for the simulations. Also, as it is now, we cannot build one replica for the entire city, as it's too heavy. It's too heavy and too expensive for the computers that we have. So what we do is to calculate the density of the buildings in that area, and based on that, we define the size of the tile. So it's more like a dynamic calculation. It's not a fixed area that we use for each tile. And one of the things that we tried was to use dynamic resolution to reduce the computational time. So instead of doing the simulations hourly, we tested if we can do it every 4 hours. And the problem remain. I think the more complex the buildings, the bigger they are, and the more dense the area is. Even though if we change the resolution, we still are not able to compute all the buildings before the next update of the database. So what we're doing now is to just reduce dynamically the area of impact of each tile. What we are able to do is to have a building classification, and this is also done automatically based on the databases that are built. This is the Gulhaden. Also, with the data that I mentioned before, we can estimate the population for each building, and also the different type of circulations there are in the area, and these are the main sources of information that we use to understand if the building environment is friendly to elderly adults. One of the things that we do is to compute the distance from a specific building towards important destinations such as pharmacies, clinics, grocery stores, parks, and based on the distance, we compute different levels of risk. We consider if there are benches on the way, the lighting that is in place, the type of surface, the thermal comfort. And based on those results, we score how well placed is a building and how friendly is the connection that they have. Also, the slope of the trajectory. So the more dangerous paths are there, the lower is the score, the surrounding environment. These are the results from the study. We analyzed the different heights and the terrain. We also did some cluster based on the population and the similar characteristic that the building have to form groups of buildings based on the connections and where they are allocated and the number of users that they have. And based on that, we calculated how friendly and how easy access this building have. In the last image, we see a heat map of circulation, and this is only done for early adults from each building. And what it plots is what is the most likely path that it will take and how dangerous it is. Based on weather conditions, slope, and the things that I previously mentioned. This will be the conclusions of my presentation. From the project that we saw at the beginning, we learned that the digital shadows are able to consume the same 3D models, even though they are from independent simulation software with different domains. Also, we saw that it was a great improvement to use pressure coefficient instead of a tabulated infiltration. The difference between the energy demand they were very different since they are not using a fixed value, but it's a wind-dependent calculation. Also, the use of the visualization tool, it was very beneficial. We were able to present our results to our colleagues and people that are not in the field of built environment, and for them it was much easier to understand the impact of the results. Also, one of the things that we learned, it was that we need better standardization for automations like the ones that we did. There is a lot of different formats and inputs that the domains use, and that could be interesting work to do in the future. Also, we consider for future work to add other variables that could be interesting as well, such as rainstorm, sky view factor, daylight, and outdoor thermal comfort. Also, I think it was challenging to find a way to weight the different results from the different tools that we use. Um, um, that I think it could have been done better, not just to use a percentage, a way to compare them. I think we could add other indicators, and I think if it's something that if we continue with the work, something that I think we would like to improve. And with this, I finish my presentation. Thank you very much.
Thank you, Alex, for this fascinating dive and a lot of nice videos and pictures and a lot of work behind it, I'm sure. For the audience, I forgot to mention earlier, but you can put questions into the Q&A and I'll read them to Alex and for the rest of the audience because most of you cannot see them. So feel free to do that now while I start chatting with Alex on some questions that bothered me or were popping up while you were presenting. Yes, so this notion of digital twin, and I'm glad you showed this many different layers in the beginning, and also like in the beginning you honestly said like some of it is like a digital shadow, and so I think we overuse this term a little bit. I don't know what your feelings are on that or where you stand. The way the term originally was thought is that it's a two-way link between what happens in the computer and what happens in reality. And somehow for operating a building, that kind of makes sense to me. But how would that even look in like an urban design type thing? Like how do you create a twin that feeds back into reality when you talk about urban design? Like, I don't know, what is your thought on this?
Um, I think, like for example, for um, buildings, they have sensors on the walls to um, close some windows. That I think normally they don't work. And I think if you have a digital twin that not only analyze one facade, but the entire area, maybe it will be more accurate. But I think it's more relevant for other kind of analysis, like maybe transport. Uh,
Hmm.
you can maybe easily update the communication between different connections. And but for energy purposes, I think it's a bit hard. One thing that we were considering it was to uh, use smart meters, for example, and if you have solar panels, you can send some kind of signal to advise to use energy expensive task or not. So depending on how the grid is
Mhm.
in use. But I think in general, for urban environment, I think it's more related to transport. I think that's like a clear win, I think.
Yeah, that makes sense. That I understand that too. Um, and then the next question that is quite, also logical that follows from when I see work like this is, say I wanted to do this in a different city, like somebody, you did this in Gothenburg, but somebody in, I don't know, Aalborg or whatever, Berlin sees this and say, "Oh, I want to do this as well." How do you even start? Like what, like it's so much it seems. What is like, is there like a step-by-step instructions or how did you get started and how did it get into where it went?
You
So
mean with the twin replica?
yeah,
The
for the first paper that you showed or the initial paper.
Ah, okay.
for
Well,
example?
for us, since we knew that it was an area that was going to be intervened, uh,
Hmm.
then it was easy to convince the others experts in different domains to jump in because they also found it interesting. They also didn't know what will be the results. Uh, I think if you find similar conditions in another city where you're wondering what will happen if we do this, then it makes sense.
Yeah, I think my question was more towards the technical alignment, right? So you have a lot of different data sources, and I think some places have them and some places don't in some ways, right? So that is sort of like a prerequisite is to collect a lot of data on all kinds of things before you can fuse them, right?
Mm.
Um, so with that, what about, training of engineers or architects to build such a structure? Like, do we need to rethink our education? I'm asking that as an educator. Like, do we need to rethink how we teach what we teach to go even more into detail with data? Or is it something you can pick up later? What do you think? No
Uh,
questions for you today. Sorry.
I think it's very interesting to teach students about how to read simulations, for example. I think most of the training that we do is how to use the softwares. And I think, of course, there are some evaluation on how they understand the results, but I think experience helps a lot. I think you can see data in different ways depending on the knowledge and experience that you have. For me, while I was working on the project, was also very interesting to learn about noise simulations, for example, or the wind comfort, and which is outside my expertise. Um, but I think it was very interesting. And I don't know if there are programs that combine different aspects. I think for us, it's more like daylight, energy, comfort. But there are, I think the other domains are left for other type of professionals.
Yeah. Yeah, yeah, that's true. I think it was the first time I saw also, not the first time, but it's not often you see noise and things like that. So it's very interesting.
Mm.
They're also fascinating on that end. A question from the audience is, did you consider other schemas or ontologies like Break IFC or CityGML for data integration?
Um, we were trying to find open source data sources. We could use CityML, but um, I think the one that most people use is OpenStreetMap, and I think what we wanted to do is to find data sources that are worldwide.
Yeah.
Um, and I think OpenStreetMap, I think in Europe is very good, but if you go to other places, yeah, they don't have any data, or even the 3D models are not there.
Yeah. Do you think, and I think this is also where that question went a little bit about, I mean, Brick is about building operation and IFC is the BIM design and CityGML is on the urban scale. I think it seems to me that a lot of work you spent on was integrating data from different sources into like a common denominators, overall schema or ontology. Like, would you say that that is a big challenge to get all these data sources to talk to each other? And do you see any standards emerging that help with this, or is it going to be every time, every project doing their own thing, basically, and then hard to reproduce and or learn from in that sense?
Mm, yeah, I think it's hard to find one database that fits everywhere.
Yeah.
Um, I think that, for example, for the transport database that we have is unique in Sweden, and if we want to incorporate that in a different place, then we have to find a way to get that data. I know the Google has a lot of APIs where you can get some information, but then you have to pay, and so I think the tool that we build is designed so if you have the data, you can plug it in, or if you have an API, it will recognize it easily. But yeah, I think that's a major challenge, how to find information, and especially real time.
Yeah, for sure. Yeah, that's really hard. I do have some more question on the results in the first one. Like for example, you also mentioned right that I think you said it every alternative in that first example increased the energy use compared to the baseline. How do you why should they decide to do all the alternatives if it's going to be the most expensive solution, assuming energy is the most expensive carry in the end? Like, how do you argue this result in the end? With
But the energy demand wasn't for the one that we calculated. It was for the existing buildings that were already there,
uh-huh.
not for the alternatives. The idea was to see how if that place changed, that which now is empty, and if we put some new buildings there, how the existing buildings will have an impact. So yeah, in all the scenarios, it will be a negative impact. It will end up consuming more energy.
Sorry, yeah, I misquoted my question, but but so you will have a negative impact on the surrounding, so that's kind of a hard sell. But
Hmm.
we want to build housing, right? So how do you argue this? Uh, I'm curious. Now I don't know the answer.
I don't know if they take into account. I mean, I think they don't know what will happen to the
Mm,
existing buildings. Um, so yeah, maybe if they read the paper, then we'll think twice if if they should do that.
right. And
But
maybe Wayne, like just for the final question, I don't know if there is more coming from the audience, but um, similarly, like I don't know if I forgot if you have tried or not, but obviously there is climate change impacts, and once you build a building, it will be there for a while, right? So does it make sense to evaluate energy and urban heat island or something like that 10 years down the road or 15 years down the road with changed climatic conditions and see what that would feel like? Because we already know we're going down a certain path, and the TMY files are not necessarily a very good indicator of how things will be in 20 years, right? So I don't know what your thoughts are on that.
well, in Chalmers, there were some researchers that were looking into climate change and how it will impact in Gothenburg. And I think from the presentation that I thought, they didn't agree. Like one position was saying that we might have issues with the heating islands, while other researchers said it will be almost impossible. So it's hard. I think it's predictions are other type of simulations. I think it depends a lot of the inputs that you're using and how hard you think the climate will be in the future.
Mhm.
Um, but yeah, I think it's all about the data set that you're using, and in the case of Gothenburg, I think um, it's a lot of green areas, and I think here when they do some changes in the city, they consider how that will impact in the future. This example of densification that I presented, it was a parking lot, which is yeah, just a concrete slab, and I think it will improve the environment if they put something else there.
Yeah, immediate improvement. That's true. Okay. Alex, thank you very much. I enjoyed this a lot. We're at time. So with that, I thank you and thank you for the audience. And I hope to see many of you again in 2 weeks on June 12th when we talk about impact pathways. Thank you.
Thank you very much.